Oh, well, we're gonna have to look. Sorry. All right, here's an example of a 500 millibar chart. And in this case, you notice that the ISO heights are nearly parallel. See the black lines? They're nearly parallel to the isotherms, which are the dotted red lines. And that tells you that they're not moving a lot of warm air from place to place. So there's not a lot of cold and warm air advection here. So if this area of colder temperatures was over here just a little bit more, these cold winds would be pushing them to the south. Let's see what else we wanted to look at here. So the station plots show temperature, winds, heights, and often dew points as well. Let's look on this next chart, see if we can see dew points on here. Yeah, so here's the temperature is -15 up at 500 millibars here, and the dew point is -20. So this air is not saturated. Over on this side, here the temperature at 500 millibars is -23, but the dew point is almost the same. So this is some fairly moist air right in this area here, out in front of this trough. And this is a low pressure area here. So, and here you have, I think the next chart, the next slide may say it, but you see you've got convex concave pointing at the North Pole where you have a ridge of high pressure. And down here you have more of a, I'm getting ahead of the next chart. All right, let's go back. So as we were saying, station plots show temperature, winds, heights, and often dew points as well. Rather than highs and lows, we talk about ridges and troughs. Ridges are where the iso heights are convex to the pole. Troughs are where they are convex to the equator. So like a little half moon shape, right? A little kind of circle shape, either convex to the equator pointing south or convex pointing towards the pole. Well, that's a ridge. The troughs, a lot of times where a lot of the heavy weather happens right in front of the troughs, that's where they're convex pointed to the, in our case, the south, pointed towards the equator. There are sometimes closed iso heights, which would be called highs or lows, and upper level charts can give us clues about what will be happening at the surface. So in this case, you could tell there's an enclosed low right here, and the temperatures, look at the temperatures, -32, and that's about the coldest temperature you can see on here, and that's going to indicate it's got some low pressure happening at the surface. And that's going to be some, and you see how strong the winds are on here. You see where the isobars are tightly packed like this? You see how close together these lines of equal iso heights are? I shouldn't say isobars, iso heights. See how they're all kind of packed together right here? And you notice if you look at the sensing of the wind is strong. There's 50, 60, 70, 80, 60, 70, 75, a 75 knot wind out of the north here. That's a pretty strong wind. Whereas out here, where the iso heights are not really very close to each other, there's not a big pressure difference here between these areas. Wind's only 25 knots. Down here, down at the base of the trough here, you can see the winds are blowing still at 50 out in front of it. But once you get into the area right here, where a lot of the weather will be happening down here, the winds are really strong. They're bringing that cold air from the north, filling in, to the cold front down here. What does temperature advection mean? In the upper level, temperature advection is the change of upper level temperature with time due to winds. So the wind blows cold air in or warmer air in, and that is called moving the air or advecting it from one place to another. As the temperature increases, the density and therefore the weight of the air decreases. lowering the surface pressure. Remember that last one? We said this is a low pressure down here because you got some cold air moving here. As the temperature, the opposite of true of negative temperature advection. So bringing in temperature increases the density, therefore the weight of the air decreases, lowering the surface pressure. But if you bring in negative temperature, now the weight of the air will increase, and that will cause your higher pressure movement. As the surface pressure decreases, low pressure systems can form or deepen, which means that the lower central pressure of that circle, which we're talking about right here, is getting, the pressure is getting even lower there. So causing a lower central pressure, that's going to mean a deepening low, which is going to mean more intensity. If it happens in winter, could mean we get a whole bunch of snow out in front of it up in the Northeast. So if you look at the previous 500 millibar chart, it shows very little temperature advection since the iso heights are nearly parallel with the isotherms. You look back at this chart here and look at these dotted lines here of equal temperature are parallel to the iso heights. So right in this area, you're not bringing in a lot of advection. So weight is a force, and force, if you want to calculate what a force is, it's a mass times acceleration. So in the case of pressure force, gravity is pushing that air, is pulling that air, that column of air down towards the ground, and that's what's giving it force. And that's why you call it a force, because gravity is the force that is pushing or pulling that weight of air towards the center of the Earth. Upper level global circulation. If we look at the upper level circulation from above, the North Pole, we can see a system of ridges and troughs called Rossby waves. So do we see these? See how there's like a zigzag like this, and at 300 millibars, that's even more pronounced. So that's where we get these Rossby waves. Just like you're sitting on the shore and there's these giant waves coming by. That's what's happening, rotating around the North Pole in a circle. The big question is, if this ice pack melts, how's that going to impact the Rossby waves? And I don't have an answer for that one. Probably need to go back to school, right? So here you see a ridge. Remember we told you that ridges are convex towards the North Pole. So ridge means warm air, high pressure, it's moving to the north, and that usually means better weather, good weather, versus a trough right here, just like a feeding trough for horses or cows or pigs. It's like a U-shaped affair here. A trough indicates that there's cold air and there's low pressure and it's trying to move south, and it often means bad weather. So if we look at the upper level circulation from above the North Pole, you can see this system of circles on a pressure map, and it kind of sticks out. It's pretty cool. And those are called Rossby waves. Usually there's 5 or 6 of them. Also, they're called planetary waves. So, you know, there's a limited number of them. You know, the limited number of troughs. You know, sometimes you get like little zigzags in it, or little energy coming down from Canada. They call those clipper systems coming through and bringing some snow here in Chicago. Normally, there are from 3 to 5. It's rare to just have 3, but pretty common to have 5. And they travel around the globe going from west to east. So if you were to watch this upper level circulation chart over a number of days, it would just be like watching a creek next to your house. You just see the same waves going over and over again, caused by different things. And that's the number, those are Rossby waves. Well, what is convergence and divergence? Well, convergence, what does that mean? It's kind of coming together, right? Divergence means kind of splitting apart. So here in this scenario, the air is starting to pile up. So here, just like these guys are coming in from the west, these guys are coming in from the north, they're kind of on a collision course. And as they come together, they kind of get in each other's way. So some of the air gets forced down. And so as it forces air down, where the air converges aloft, that's going to cause higher pressure down here. So here you have higher pressure, And as the air piles up in the upper atmosphere, it's going to push down because that air that air takes up space. It needs someplace to go. So as the air converges or convergence aloft, it's pushing down. And as it pushes down, it causes higher pressure at the surface. And that's going to mean air is going to try to flow outside from this, and you're going to have probably better weather. Convergence means the winds are coming closer together or slowing down. Divergence is just the opposite. So here's one of those Rossby waves, right? In our imaginary atmosphere. Here's a Rossby wave. Here, the air is splitting apart. Now, as the winds diverge and go in two different directions, well, they're like a vacuum. They're going to suck the air up. And down here, the air is going to start to rise. And as it starts to rise, it creates a low pressure system on the surface. So here, the winds are speeding up as they got more room to play. They're taking off in opposite directions. And as that happens, the air starts rising underneath it. So that's going to cause a low pressure area, and directly underneath divergence aloft, that's going to give energy towards an airflow around it. And here you got a little warm front depicted at the surface, and over here is a cold front. And this is in the middle of the country. This isn't so much down in the Caribbean, because you don't get as much in these low pressure areas working through there like this. Convergence increases pressure, so the weight of the air above was pushing down when these two masses of air got closer together, and they started to slow down because they're kind of getting in each other's way now. It's like on a highway when there's a traffic jam there on I-95 or whatever highway's near the house there, 70 or 80. All of a sudden, all the traffic slows down because everybody's in each other's way. Now here, when they're out of the construction zone, zoom, I'm going to take off in the upper atmosphere. And as they take off and increase speed, they suck that air out from underneath it, causing this rising air and a low pressure at the surface. Convergence increases pressure and that deepens the highs. Divergence decreases pressure and deepens and increases the lows, creates lower pressure. It's kind of a tricky one, but it's clear. All right, that's pretty much all for this chapter. In atmospheric pressure, it's caused by the weight of the air above it. And that weight is caused by gravity, which we talked about. Standard sea level pressure is 29.92 inches of mercury or 760 millimeters of mercury. Another way where it's commonly measured is 1013.25 millibars, or also known as hectopascals, or 14.7 psi. I would say each of these numbers is worth your time to memorize. So you should probably know these numbers back and forth. So get you some flashcards and say, what is standard sea level pressure? Each one of these answers is going to come up again. Pressure is measured by barometers. We talked about the two different barometers, the aneroid and the other kind, and they need calibrating to make sure they're accurate. The measured pressure is reduced to sea level. So we talked about high altitude airports like Denver. The pressure is going to be less there, but there's a correction factor that they add that allows them to compare the atmospheric pressure to the surface pressure in Kansas City. That way they know if there's high pressure over Denver or low. So that pressure is reduced to sea level so that can be corrected for altitude. We talked about pressure gradient force, and that is the pressure difference over a distance. So as we talked about, if it was only 500 miles apart, you could have an 80-mile-per-hour wind if there was only half an inch of mercury difference. But if it was 1,000 miles apart, now the wind's still windy at 40 miles per hour, but it's not as intense. So increasing the pressure gradient force increases the wind speed. Again, talking about higher, bigger differences in pressure, a lot more speed. On your surface charts, when you have isobars that are close together, that's going to indicate strong winds. Isobars are lines of constant pressure. On surface charts, highs and lows are centers of those surface pressure features. Winds are always referred to by the direction from which they blow. So the winds at the surface will circulate into lows and out of highs. What they talk about, because on the surface you have frictional effects, but the circulation around a low is going to be, let's go back and look at that picture. So here where you have a low pressure at the surface, here, you got low pressure at the surface, and it is going to circle around it like this, or cyclonically in the northern hemisphere, like a cyclone is counterclockwise. Yeah, you're gonna have to memorize this a lot. So clockwise around a high, or anti-cyclonically, counterclockwise around a low, or cyclonically, or like a cyclone. Counterclockwise around a low in the northern hemisphere, or cyclonic. All right. So in the northern hemisphere, it is counterclockwise circulation is called cyclonic around a low, right? Clockwise circulation is called anticyclonic, like around high pressure. So in the southern hemisphere, it's the opposite. Try not to get confused. Don't get too much into this, or else it'll confuse you. Worry about Australia. Most of the questions are about northern hemisphere. They are measured by anemometers. That's how you know how strong the wind is. In the absence of friction, pressure gradient force is balanced by the Coriolis effect, and the wind tends to blow along the isobars because as the wind speeds up, Coriolis effect starts to take place and turn it to the right. However, in the opposite direction, pushing, if the wind is coming like this, you get your Coriolis wanting to make you go right, the pressure gradient force making it wanting to go left, and so that wind blows along your isobars at the surface. So once you include friction, it causes the wind to blow slightly across the isobars. Not completely. It's not going to fill in that low pressure, but it'll blow sort of inwards towards it, so that, remember how it says that face it when the wind is in your face, you stick your right hand out. Well, at the surface, you've got to point a little bit backwards because you have those friction effects, right? And that tells you where the low pressure is. Changes in wind direction with time are called veering if the direction changes in a clockwise manner, and backing if the direction changes in a counterclockwise manner. So just remember, veering indicates it's tick, 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 it's going around, and the direction is coming as the wind changes. The Weiss-Ballot law shows the direction of the low, and that's, you can impress your friends by using that at parties. Face the wind, the low is to your right or slightly behind. Don't confuse, just don't read this line because it's just confuses you by saying it backwards. There are many kinds of local winds. Two major winds are the sea breeze, when the air is blowing towards the land, and that's due to land heating during the day, or land breeze when the wind blows away from the land. So sea breeze, it's blowing in from the sea. Land breeze, it's blowing out from the land. So that's due to land cooling faster than water at night. On upper level charts, lines of constant altitude are called isoheights, because remember on those charts, the whole chart tells you 500 millibars. The height above the ground is how high you have to go in the atmosphere to find that pressure. Ridges are where isoheights are convex towards the pole. Troughs are where they are convex towards the equator. Around the entire planet, you have a series of troughs and ridges, and it connects all the way around the world. Sometimes you have close lows and highs, but around the pole, those are called Rossby waves. So, John Tonetti, how many Rossby waves are there usually going around the world? You got to unmute yourself too. I didn't tell you about that part. Go ahead and unmute yourself for a second, John.
Rarely 3, typically 5.
Typically 5. Excellent. Upper level convergence raises surface pressure, while divergence lowers surface pressure. So that it's a tricky concept, but it's really cool. If you have convergence aloft, you know, it's like the freeway when there's too many cars, it slows everything down and it pushes air down, which causes high pressure at the surface, and the opposite if they're splitting. All right, I'm going to pick on everybody. Let's see, I don't know who that is. Can't pick on you. That's smart. Bill Madison in millibars, standard sea level pressure is. Oh, you got to unmute yourself, Bill. That's the other surprise.
Sorry about that. 1013 point something.
2.5. Very good. John Zills, a north wind blows. Yeah, unmute yourself, John.
The north wind blows from the north.
From the north. Excellent. Steve Boyer, the most important correction to surface pressure measurement is due to, unmute yourself.
Altitude above the sea level.
Excellent. Elevation. Altitude above sea level. Well done. Pat Mussman, the force caused by the difference in pressure over distance is called what? Expert, you want me to go on, Pat?
Yeah.
Angela D, the force, unmute yourself, Angela. The force, you can turn your camera on too, so I can tell you're watching. The force caused by the difference in pressure over distance is called what? Angela, go ahead and unmute yourself. You there, Angela?
Yeah. I'm on my phone. My computer is just up and down, up and down. Yeah, what was the question again?
What is the force? The question is, the force caused by the difference in pressure over distance is called what? Talked a lot about it tonight.
I don't remember.
Oliver T, the force caused by the difference in pressure over distance is called what? You got to unmute yourself. What was that?
Can you hear me?
Yeah, now I can hear you. Go ahead, Ed, Oliver.
Pressure gradient force.
Right on. Well done. Ed Hallen, what causes?
Just this one can get confusing for people. So just think of an acronym or something for that PGF, like Procter & Gamble, professional golf, or something. So then you remember which order the PG and the F go.
Good. Yeah, we'll take all the help we can get. Did I say Ed Hallen? Did I already pick on you, Ed? Did I pick on you, Ed? Ed, what causes surface winds to cross isobars?
The Coriolis effect.
No, it's something else that causes the winds at the surface. What else happens at the surface?
Friction.
No helping. Ed, that was for you. All right, Ed, I'll give you another one. Correct. Friction is correct. Ed, how about the next one? Winds that flow clockwise in the northern hemisphere are called what?
Cyclonic.
Those are the, remember the ones around the low are counterclockwise, right? So this would be anticyclonic, right? Angel Betancourt, when the wind direction gradually changes direction in a clockwise fashion, it is said to be, ooh, this is a good one. If I put you asleep, Angel. You gotta unmute yourself, Angel. You there, Angel? Angel, you there? Jeff Link, unmute yourself. The wind direction gradually changes direction in a clockwise fashion. It is said to be only two choices. You there, Jeff?
I'll take it.
I'm trying to pick on everybody here. Bob Mack. You there, Bob? You know, it's funny when I start asking questions, a lot of people leave. That's really funny. You there, Bob Mack? Unmute yourself.
I'm here, Bob. I just had a hard time unmuting. That would be varying.
Veering is correct. Well done. Jack Benton, isobars are lines of constant.
Constant pressure.
Excellent. Dave McCullum, the jet stream shows up best on which upper level chart? That's a good one. Go ahead, Dave. The jet stream. You remember which level chart that was? Which millibar chart?
Yeah, I don't remember the name of it. I'm sorry.
No worries. No, that's the jet stream is correct, but we're looking for Bob Wokey. You know this one off the top of your head?
I'm thinking 300 millibars.
300 millibar. Well done.
Right.
Mark KM4EMD. I'm not sure who that is. Lines of constant temperature are called.
Isotherms.
Right on, well played. Sean Buckmaster. We're not picking on you, Mr. 96. Johanna Wood. Surface pressure is caused by. Johanna, you there? Sean, I know you know the answer. You got a 96 on the test. Go ahead, Johanna.
I don't know.
Gilbert
I
Thomas, you
can't
want to take a crack at this one? Surface pressure is caused by what?
Hey, Bob, can you hear me now? This is Jeff Link.
Jeff, take a shot at this one. Surface pressure
Yeah,
is
thank
caused
you. I
by,
think it would be the weight of the atmosphere above it.
right. And what is that called?
Pressure.
Pressure is correct. Well, the weight of the air above. That's what they were looking for. Well, that surface pressure, right on. All right, Gilbert, are you there now? Isobars on a surface chart are drawn every. Now you-
4 millibars.
4 millibars is correct. Well done. John Puskar, higher pressure gradients cause.
Strong winds.
Strong winds. Well done. Dave Bobos, the standard instrument for measuring wind direction and speed is called what?
Anemometer.
Correct. Michael Richard, half of the total mass, it should be an O, half of the total mass of the atmosphere is in the lowest. I spoke over this real quickly. You had to read your book pretty good to get this one. You there, Michael?
I'm here.
You remember this one?
Half if the total mass of the atmosphere.
They're looking for
is the-
altitude here. If you're a pilot, it's the flight level. That's where the flight.
Oh, 18,000 feet?
Are you a pilot?
No.
Oh, okay. Well, 18,000 feet is correct. Well done. Chris McNamara, do you have any questions?
I do not.
Well, good, because I've got questions for you. We're going to go through the questions in your book now. There's a lot of debate over this, which makes this class fun. Tell me, number one, a north wind is one that is
Coming from the north.
good. Pamela W., did I call you yet? Pamela, wind speeds on charts are given in
Knots.
good. Joe Thalheimer, standard sea level pressure is
14.7 PSI.
excellent. Jay Zimmerman, number 4, if the barometric pressure is measured in Albuquerque, New Mexico, the most important correction to make before reporting it is
Has to be calibrated for altitude.
right on. Answer D, correct. Catherine Nixon, station barometric pressures are reduced to sea level. You there, Catherine? Can you hear
Yeah,
me?
I'm here. What number are we on?
Number 5. If you want to pass, you can pass. Station barometric pressures are reduced to sea level. Why is that? It's not a very well worded question.
I'm gonna pass on that one.
All right, Dave Watkins, you got that one up your sleeve? You there, Dave? Yeah, unmute yourself, Dave. You there, Dave? This is fun. Well, I don't know if you guys got the same list I did, so only I know who I'm calling. Addison, how about number 5?
I had C,
C
I
is
had-
good. Is that who answered that?
Bill Madison.
Oh, Bill, you're jumping in. It wasn't your turn. Addison,
Oh,
how about
I
the
thought
next
you
one?
said Madison. Okay.
Oh, my bad. Oh, you're right. I did. Addison. Addison,
Yeah,
with an A.
That's okay. Yeah, he can take that one. I'll do the next one. I don't care. He already answered it.
Android barometers are more useful on both because they
Can be mounted in any position.
Yeah, who has 29 inches to fit that other thing? Number 7, Danny Mullen, unmute yourself. Pressure gradient is defined as?
The pressure change per unit distance.
Right on.
C.
Correct. Eugene, number 8, unmute yourself. The primary force generating wind is? You there, Eugene?
Borealis effect.
That's Gene. That's wrong.
Bob, I'm back. It's
Hey,
Dave
Dave.
Watkins. I'm back.
Well, your perfect timing. Number 8, the primary force generating wind is? Number 8. You got your book in front of you there, Dave?
I'm in the study guide right now. Hold on.
All right, we'll come back to you. Eugenia there? Joe Jackson, number 8, the primary
No.
force. You there,
Bob,
Eugene?
I got it.
All right, go ahead, Dave. Number 8.
Number eight is C. Temperature gradient.
No, they're looking for.
No. It's D. Surface heating.
No, looking for pressure gradient force. Remember we talked about that bag of air getting pushed, and that's what causes the winds, right? So different things influence the wind, but it's the pressure gradient force. If there's a big difference in pressure, that's going to cause big winds. Joe Jackson, number 9. The effect of friction on the wind is?
I had D.
The wind blows across the contours. It's a tricky one because what they're looking for here, remember we talked about at the surface, because the Coriolis force is less, because the wind speed slows down, that's going to mean the pressure gradient force stays great, and that's going to cause the wind to blow across those contours instead of along with them. So they're looking for friction slows the wind down. You're going to need to remember that one because you're seeing that again. Friction A slows the wind down. Bill Luckshaw, number 10. Cyclonic wind flow is?
Clockwise in the southern hemisphere.
Yeah, that's a tricky one. You have to go back and think. Thomas Cantus, number 11. The jet stream is? Unmute yourself, Tom.
The jet stream is a high altitude wind current, C.
Absolutely correct. Amy McPherson, unmute yourself. 12. If an observer is facing the wind in the northern hemisphere, the low pressure center is approximately Amy? To the right. To the right. Was that Amy? Was that you?
Yes.
Good job. Greg Schaefer, number 13. The vice ballot law tells us. Unmute yourself, Greg.
I don't have my.
Oh.
Say the number again. What
Number 13. The vice ballot law tells us.
I've been answering them in my head. I don't have the
Location of the low pressure.
Greg, your voice changed there suddenly, but that's correct. Jock, unmute yourself. Jock Wilson.
Yeah, C, location of low pressure.
Right on. A wind gradually changing in a clockwise fashion is, Jock?
I see. Yeah. Veering.
Veering is correct. Well done. Who haven't I picked on lately? Monique, number 15. On the station model, a plotted pressure of 853 is, a lot of people had trouble with this. I don't have trouble with this.
B 985.3 millibar.
Excellent. And if you look on page 20, you see right next to it in the back of the book there, it tells you in parentheses what page to double check it. Dean Christie, number 16.
Can I say something real quick?
Go, who is it?
This is Mark
ahead,
Bagley. What is the point of dropping the first digit off? Why do they do that?
It's the space on the chart. Otherwise, the chart would be way busy. There's a number of different things that are done on the charts. Like they use those little triangles versus just writing the wind speed.
Right.
Visually, I think they think it's easier to understand that way, if that makes any sense.
Okay. I mean, I can remember this. It just seemed odd to me.
That's an excellent question. And on chapter 7, if Mike shows up, boy, you're going to be right there to ask him that question. You're going to tell him whether or not you like the idea or not. So, where were we? Dean
We're
Christie.
about to ask 16.
All right, Dean Christie. I'll give you 16, even if I had already. On the station model, a plotted pressure tendency of minus 2.6 is
A fall of 2.6 millibars over 3 hours.
Yeah, you guys remember that 3-hour trick. All right, when you see it on that station model, because if you say just over an hour, you're going to get that one wrong. Good. Richard Voss, Number 17, isobars are lines of constant. Unmute yourself, Richard.
Oh, go home and get some rest.
Okay, isobars are lines of constant. I'm gonna say B.
Charlie,
No, they're looking for different, or they're looking for lines of constant pressure, C.
Charlie.
Noah, how about number 18? The station model below shows.
D, a southwest wind of 15 knots.
Absolutely correct. It's like our team here. How are you, Chaz? Say hello.
Hi there.
Angela, number 19, Rossby waves are.
C, large upper level waves that propagate around the globe.
Bravo.
Propagate. Yeah, they move. Propagate is a tricky word, you know, that sounds like the Bible where it says begat, but they propagate, they move around the world. But we better not use that in this class because they wouldn't appreciate that. Ed, how about number 20? The solid lines on a 500 millibar chart are
ISO heights.
ISO heights. Angel, did you ever figure out your microphone? Go ahead and unmute yourself. Let's see, can we hear you this time? Go ahead, Angel. You there? Jeff Link, how about, are you there, Angel?
No poops.
You're not Angel. I know who Angel is. All right, Jeff Link, next one. The pattern at 521, the pattern at 500 millibar that causes surface low pressure areas to strengthen is. Wait till dang until he gets it right. Okay. You there, Jeff? You there, Jeff?
Delta.
Jeff, that does not sound like Jeff. All right, D is correct. Jeff, we will let Jeff get 22, please. The jet stream shows up best on the. Go ahead, Jeff. I know you're with me now. I can't see you nodding, Jeff. Bob Mack, number 22. The jet stream shows up best on the.
500 millibar chart.
The jet stream.
Charlie.
Yeah, they're looking for the high altitude one. So the mid-range one, the weather movement of weather would be more like the 500 millibar, but the jet stream itself really shows up there. Richard C, 23. Lines of constant temperature are. The book's got this one wrong. What's that, Richard Clemens?
C, isotherms.
Yeah, it's what it says in the back of the book, but that's actually wrong. It's actually all of them, because you can find isotherms on the upper level charts, and they are plotted as dashed lines. So everybody look at your book and get your pen out and note that 23 is actually D. You know, if it's not right on the test, you can sue me. So that's all I got. Bob Wilkie, how about 24? On the 500 millibar chart, ridges are.
That would be A, convex to the north.
Correct. Mark Bagley, number 25, surface pressure is caused by. There, Mark. Unmute yourself, Mark. You there, Mark? Flotilla 1.9. John Beckmaster, I'm going to bother you, even though you got a 96. Let's see if you deserved it. 25. Surface pressure is caused by.
Mark's here now. I got it. It's
Right.
I'm sorry. It's the weight of the air above. I was having trouble unmuting for some
No
reason.
worries. No, it's exciting. Sean, how about 26? Isobars on a standard surface chart are drawn every
4 millibars.
That's not Sean. You there, Sean?
Oh.
Is there another Sean? Maybe there's another Sean.
I'm sorry, something said John.
Oh, okay. Who is Zoom user that has not been picked on yet? Mike McGann, number 27. Higher pressure gradients cause. There, Mike, can you unmute yourself?
It's Charlie, stronger winds.
Stronger winds, right on. Johanna Wood, number 28. The polar jet stream.
Let's try C.
C is correct. Dave Bobo's 29. The standard instrument for measuring wind direction and speed is the
Anemometer.
correct. Now, who is Zoom user who I have not called on yet? I'm going to give you the last one because I want to be fair.
I'll take it.
Are you Zoom user?
I am.
All right.
Okay.
Who is this?
This is Kathy.
Hey, Kathy. 30.
Hi.
You
Charlie.
okay, Charlie. Yeah. Half of the total mass of the atmosphere is in the lowest 18,000 feet. Now that's an easy one for pilots because that's where it goes from upper level to flight levels or altitudes to flight levels. How are we doing, team?
Great.
Are there any questions?
Yes, I had some questions in the chat that the group might be interested in.
Go ahead, Samantha, please do.
Can we review dew point? So it makes sense that the dew point is when the air becomes saturated based on the temperature. So we can know when we're going to have moisture on our grass or if it's going to be humid and muggy. And it has to do with atmospheric pressure. Is there anything beyond that portion that we need to know for this class?
So for the dew points, you're throwing in a couple of things. Atmospheric pressure is, the dew point really doesn't tell you anything about the pressure. Now look here, here is a report at this altitude. Here the temperature is -13 and the dew point is -25. Those are not close together. So that air is relatively dry compared to here where the temperature is -24 and the dew point is -25. And that tells you that that air is almost completely saturated. The dew point is a measure of how close the temperature, how close the atmosphere is to being completely saturated.
That's on the next chapter.
Yeah, we'll talk more about that there. And you get one more chapter with me in chapter 3. We'll be covering moisture, latent heat, fog, and stability. Let's see if there's any more questions. I'm going to go ahead and stop sharing here.
Yeah, Bob.
Go ahead, sir.
Yeah, on 18, the station model below shows a southwest wind of 15 knots. That means that wind is actually blown into that station model from the southwest.
It's coming in from the southwest. Very good.
So bottom is south. Okay, gotcha.
Yeah.
Thank you.
Bottom is south, top is north. I threw you off a little bit with my explanation there. I got all excited about the anemometers there. Was the entire lecture recorded? Zoom user, I'm sorry. No, it was not. We recorded about halfway through, and I'm going to have to send an apology to all of our friends to let them know they're going to have to read the first chapter to figure that out. If you want, you could turn your cameras on and say hello. Anything else here? Yeah, I think that you're the user. Okay, go ahead, Monique. Go ahead.
Bob, yeah, could you explain the divergence and the convergence again?
Let's see if I can get back in here.
Please.
And that's an excellent question. This is a very, very complicated topic, divergence and convergence, because see if I can get this to go backwards again here. What's happening in the upper atmosphere is you have parcels of air moving across at high altitude. They're in the mid-level of the atmosphere, say 18,000 feet. And here the wind's coming from the north and the wind's coming from the west. And at the high altitude, not near the surface, this isn't down at the surface, this is up high. The winds are out of the north and the winds are out of the west, and they're coming together. They're squeezing together. Now, as they squeeze together, or they're converging, let me see if I can find an example on this chart of where the atmosphere is converging. So here you see the ISO heights are very far apart, but as you get down into this area, they're starting to get squeezed together. And this is up at 500 millibars. Well, that's going to tell you that underneath here, it's going to push the air down. It's going to force the air down in this area here. Versus as they start to spread out, let's see if I get a real great example. Here's a good example down here where you can see
What do you mean by pushing the air down?
So if you have the air coming together at high altitude, they're squeezing together like two people trying to sit in the same chair on an airline. They're squishing together, and that puts more pressure on that seat because as those two air masses, imagine two big bubbles coming together and squeezing. Now, as they get in each other's way, they slow down and they're pushing the air right in that area down because there's no place else for it to go. It's all squeezed in there. And when the air sinks, it increases the pressure at the surface. So it's going to either reduce the amount of low pressure or increase the amount of high pressure. So as the air converges aloft, it pushes down right underneath it, like right underneath here. And as it pushes down, it's going to cause higher pressure, maybe clearing skies. But here, as the isobars start to spread apart, like right in this area here, here's where the atmosphere at high altitude, those two air bubbles, they get farther apart, and now they're not slowing each other down anymore. So now they start going faster. And so as they do, up here you can see 50 knots, as they kind of get out of here, as they do, that draws the air up from underneath.
So the convergent and the divergent air masses, is the pressure increasing because the density of the air is increasing or because the speed of the air is slowing down, or is it both?
Both. Yeah, let's look at the explanation.
I'll probably read the chapter again too.
Yeah, no, it's kind of cool, but it's kind of complicated. So see if I can find the one that explains it better.
Yeah, I read it while I was working today.
Let's see, upper level adventure. Here it is. No, that's not moving.
For me, the picture is still the example of the 500 millibar chart. It's not changing.
Oh,
yeah.
okay. Can you guys see temperature advection on your displays now?
No.
No.
Uh-oh. I wonder if it froze.
Yeah,
I see what I'm doing.
The millibar chart.
How's that? Better?
Not yet.
No.
No change, Bob.
No.
All right. Is that any better?
I saw a change now, if you can hear me.
Yeah.
Yeah, now there's a temperature advection slide.
Okay. All right, here it is. Convergence means the winds are coming together. So here you got winds coming out of the north, winds coming out of the west, and they're squeezing together here, and that pushes air down. And it slows down the airspeed right here. Now here, the upper atmospheric levels, when the isobars diverge, or the iso heights diverge, that's going to pull air up from the surface because they're spreading apart. And as they do, there's a gap in between them, and that's going to draw air up from underneath. So convergence increases pressure. Right here, the convergence increases pressure as the air is pushed down. That's the weight of the air above, it's being pushed down, and deepens the highs. Divergence, right in this area, decreases pressure because it's sucking air up off the surface, pulling it up. And as it does, it reduces the air underneath there. It reduces the pressure because it's like imagine a vacuum cleaner right in this spot right here. Even if it's not touching the ground, it's sucking up the air directly above your carpet. And as it does, it's going to deepen the low pressure right here. How's that? Is that any clearer? It's a tricky concept.
Yes, thank you.
You're welcome.
Yes.
I hope I did justice to that one.
No, it's better now. Thank you.
Good. Samantha, your thoughts?
I'm sorry, I'm sitting over here answering questions.
Okay. You go ahead and answer one of them for us all now, since we got it up on the thing.
So I have not heard anything, I do not know if you have, about printing the slides. The only way I have figured out how to print the slides from the aux classroom is to screenshot them and print them that way if you want to. Otherwise, I just utilize my tablet, my iPad, so then I can write and draw stuff on my study guide and my slides.
So I also have Gmail, and I don't have a ton of different web emails, but I use Gmail. And if you have Google Chrome, you can actually access Google, Laura, what's it called? Google what? Content? But you can actually download the slides from
Google Drive.
Google Drive. Thank you, Monique. So you can use Google Drive to pull those slides off of the national website. I don't know how to
was
do it.
not, so we talked about this last week. So when you're on the Aux Classroom and you open up those slides, because I'm here right now, you can open the Google Slides and then it takes you to Google Docs. For whatever reason, this specific class does not show up as a presentation in there for you to print off or review. Like I have like tons of auxiliary stuff in there, the vessel exam workshops, different things like that. But the Aux weather class does not seem to download if
talking
you're
about-
not an instructor.
Oh, maybe I have maybe I'm a special person. I didn't realize that. Sorry, team. I guess you have to use Samantha's approach, which is cut and paste, and I don't know, I'm not a great computer person. Some people are really good at this stuff and I'm like, okay. Does everyone know what the key is to sign up for Auxiliary Classroom is ATWE? Is anybody that didn't know that? We got a couple new students tonight. Everybody knows that. If anybody is having trouble logging into Auxiliary Classroom, it's a little tricky. If you don't have any other way to do it, I can help you. But a lot of times your IT person, your Flotilla IS person will know how to do it, can help you. What else, Samantha? What else did I miss?
Someone asked a question, do you recall that ridiculous resilient ridge in California many years ago? It prevented rain and caused drought. Can you talk about that? So the direction of the wind, blocked wind, would have been from the west, and where did it go? South, and this was clockwise or. So I didn't know if they were someone asked if we were talking about permeation of the Rossby wave that got stuck, or if you're talking about just the Sierra Nevadas in general, which is a major ridge line that runs through California, parts of Oregon, Washington. That's why the eastern side of the Sierras are dry, because that moisture comes in, it gets blocked on that western front and dumps all that snow. Once you get over to the ridge, literally you go from green, cross a peak, and then it's a vast desert if you've ever hiked up there. So the moisture drops on that side. I don't know what ridge they're talking about, but that's my interpretation of it.
No, we're getting a little off the main topic here, but if you have an enclosed circulation, we talked about the divergence aloft and convergence aloft. If you have the jet stream converging aloft and it pushes enough air down, you can get what they call a blocking system, which is an enclosed high. And then the Rossby waves, for whatever reason, don't propagate. Not Big Yak, don't propagate like they normally would. And it ends up blocking any energy for coming into California, because if you have an enclosed high pressure over the center part of the United States, it ends up being just like, a football player blocking. There's nobody can come through. But that's a little advanced for this class. I don't want anybody's mind getting too blown. What I have recorded in this class will be available as a recording. I'm really sad I didn't remember to record it right away, but I wanted to get started on time. That's what you get, right? Other questions, Samantha? I hope that helped a little bit.
Those were the main questions. If you have IT questions and you don't know who the IS officer is, you can email me and I will help to get you logged into your auxiliary classroom or enrolled in the class. The benefit of taking this class is you will not have to have a proctor for this exam. Normally, the aux-op device courses require proctored exam. So.
All right. Well, someone asked, Zoom user. Is that Kathy? That's you, right? You there, Kathy?
It's JT.
Oh, it's JT? Okay. I thought that was Kathy. Okay. JT, let's have you hang around and we will, okay, JT, just hang around, JT. And you hang around and let's talk a little bit more. Chaz, anything else you wanted to share?
No, not at this time. Good class, and it is a very confusing subject. with air masses drifting around and Rossi waves and convergence and divergence. So just have to, the students just have to look at that, the materials in the book and think about what you told them. And that's the, how to say this, the things that initiate the weather. And then what is it, two classes further on, we start talking about air masses, which are the big things that sort of generate weather.
Yeah, Chaz is going to be helping us with chapter 4. He's very good at this section. Again, I know everybody's busy, but if you put the time, it will be a satisfaction for you. If you don't stay up with the class, this is a tricky enough class and it gets away from you pretty quick. So try to stay up to date with your reading. Try to take the time to write down your review questions. For those of you just joining us this week, a couple people just joined. And if you haven't finished this class before, print out that student study guide and write down the answers. And that way, in the back of the book, you look at the correct answers and you find them. Obviously, we found one boo-boo here in terms of that one answer number. Was it 21 was all of the above? No, 23 was all of the above. So if you didn't mark that down in your right answers, then you should. But they've recently updated this course, and I would say, did a respectable job. It's pretty good. AUXCOM needs a little help. There's some typos in that book. And our friend Rob Kump was here last week. They're working on it, which is super cool. I mean, I told them I was very concerned, and they reacted, and they're going to pursue and hopefully have that AUX-C. Has everybody here taken AUX-C? AUX-C is a pretty good class. This is a hard class. You guys should have taken AUX-C first. AUX-C is a lot more fun. It's like Vote America, but on steroids. Anything else, Samantha? Anything else from the chat?
No, nothing else.
Any other questions? Thank you all for being here. Go ahead, John.
Yeah, Bob, in regards to recording this, it's 99D or 99E.
I think it's D time. Chaz, I'm pretty sure it's D time, isn't it?
You said E or D?
Delta, D is a dog.
Oh, okay, and then for the studying, it's E?
No, that's D time too. That's your studying for an auxiliary specialty class.
Roger that.
So, Bob, so we log our own hours for this course?
Yeah, in the old days, I would log everybody's hours, and then I got yelled at for doing that. So the people that are pushing aux data to want everybody to log their own hours. Now, the other thing and this is great that you guys are here, and this is good time, and this is, the Coast Guard wants us to keep track of our time. Every hour that you submit helps you get ready for different missions. I had some cool missions last year, and training is an important part of being ready. And the Coast Guard actually calculated for every hour you put into getting ready, that saves the Coast Guard $38. So they're happy to have members who log their hours in aux data, because they say, these people are getting ready to do missions, whether it's surface, radio, public affairs, boating safety classes, like I'll be teaching on the 29th. They value your time and energy. If you don't have the skill, and I don't have a lot of skill on the computers, if you don't have that skill, you can actually fill out the old forms and hand them to your IS officer, and they're still supposed to enter them for you. So don't get too frustrated about entering your hours, because between your FC and your IS officer, those hours should get entered, because those are gold. I mean, that's money on the barrelhead for the Coast Guard, and we want to show our time and energy, what we're putting into this. So thank you very much for filling out those forms, your 99-hour forms. Questions? Oliver, how we doing? Is it clear as mud? How am I doing?
Doing fine.
Yeah.
Bob, I have a question if I might.
Please, Jack. You're welcome.
I'm confused about the basic issue is that circulatory flow with the land breeze and the sea breeze. Samantha, I asked this question, Samantha answered it. I'm still not clear in my own head about the relationship there between the heating air over the land, let's say in the case of a sea breeze, and the barometric pressure in that place. isn't the warmer air by definition aren't you talking about high pressure there?
So this is a unique local special effect. You have the land, you got the water. The land heats up quicker in the sunshine because the sun doesn't, some of it is reflected off the sea, some is absorbed at lower levels of the sea, but the land heats up like a microwave oven. And so the air starts to get hot and rise over it. And as it does, the air from over the sea goes in to fill that spot underneath it. So now you've got a land breeze. The breeze is caused because the land is heating up. So the water comes in off the sea. Now, during the night, when the sea is still warm and the land has cooled off because it is radiated off that energy, now the air starts to rise over the water, and the colder air over the land starts to fill in where that air rose from. And so now you got a circulation going like that.
I got all that. I'm just curious about whether there's any relationship there to atmospheric pressure in any of those effects.
I have a good answer for that because it's more of a local effect, right? Because as the air rises,
wouldn't you have lower pressure and warmer air?
I would think so.
Yes, the warmer air over the land has lower pressure locally and will therefore, because it is rising, the pressure is lower and the air from the sea is drawn in. And then at night it reverses and you have slightly lower pressure out over the water.
Okay, that makes sense to me.
Well, you're lucky you got Chaz teaching chapter 4. He's very sharp.
Okay, thank you. I think I've taken.
I thought you were asking about a different slide that was on the veering and backing winds. So that's
no problem.
Different.
Thank you for your efforts throughout this course. Okay, I'm going to sign off now. Thanks, everybody.
Yeah, I know some of you guys on the East Coast, this is hard to stay up this late at night. So I sure appreciate you guys being here. Stop shooting.
There you go. There's the picture we were talking about. Also, veering and backing winds are very important to sailors.
You know what, that weather slide, that effect for offshore or onshore wind is also important for, besides, it's really important for surfers. So that's why you'll see surfers more in the morning and the evening, because you want that offshore wind because it helps keep the crest of the wave up for a better ride.
Good. Other questions?
Hey, Bob, I got a couple of questions.
Go ahead, Steve.
In the diagram where it shows the station, this would be on that page 16, where it shows the pressure dropping, the 2.3, or they say 23 millibar. Okay. There's that slope, that slant on the back side. What is that supposed to represent? That line.
I don't have a good answer for that. I probably should know this. I don't have a good answer for that. I'm sorry.
Okay. And my other question that confuses me, and I don't know if this is from my profession of being quality control, but when you look in when they talk about how they do the rounding, where they talk about dropping the first digits off, they show the 1013.25, rounding it down to 133 millibar. But in the other example, they show 99 or 996.5. Running it. So why in one value they have 2 decimal places and the other one they only have 1?
So that's the convention. But no, notice that it's a 9 or a 10. They're pulling off the front, right?
Yeah, but what I'm trying to figure out is why after the decimal place in one they're showing 0.25, and the other one they're showing 0.5. Is there some kind of?
I have to look at that. Let's go back here, see if it shows it better. It's not going to show better there. No, that's it. Pretty much you got to read what it says in the book, but they're either dropping the 9 or the 10 off. And this the first digit is either going to be a 9 or a 10, right? So it's not like there's a lot of different choices. It is confusing in terms of the 9 or the 10, because one is 2 digits and one's 1. But pretty much
Right.
the first 2 numbers are going to be the first 2 numbers to the left of the decimal point, right? For
Right.
either condition.
Right. So
And
my
so-
question I'm asking is why in the one you're showing right there now, the 996.5 millibar, all right, why wouldn't it be, you know, they have the other example be 996.25 millibar?
So, and they must round that, right? Because it's not going to be,
Yeah,
it's not going to be a 2.5 out here. It's going to be a 3, right?
Right, so that's right. So in the other example, they had 1013.25, which they by rounded to 133. Because by your rounding in math, we all learn in in school, the 2 would round up to 3.
Right, because it's 5.
So they assuming there is no number after the 5 in the other example. I just
No, it's not assuming that there's no number after the 5. It just has to do with moving the decimal point to either the tenths or the hundredths. So you're moving it twice. So on 16, you're dropping that 1 and that 0. But if you were to, you can't have a half. So if you were to drop the 5 to drop that off because it's a half, and you would have a 2, and you move your 2 decimal points, it wouldn't be correct in my head. Because then you would.
Okay.
I don't have page 20.
It makes sense in my head. I don't know how to put it into words.
I guess, you know, for my being quality control, I'm like all the time, I'm looking at it as, okay, why in one example, they give you a value that has 2 decimal places, and the other one, they only give you a 1. Why would they not give you a 2? And so they're showing the rounding the same way.
I think
Because
that by
the
having
one
the
that starts
first
with
2,
1,000, you would drop the 2 decimal. You have 2 decimal point, 1 decimal point, but it moves twice rather than if it starts with a 9. It only moves once.
otherwise I think it'd be comparing apples and oranges, right? Because you're deleting everything from the left of this first 2 digits from the decimal point. And it seems to me that would make it easier to compare, but that's just the convention. That's how they do it. So I hope it's clear.
You wouldn't by chance have like other examples, like some meteorology charts where they've done that? So
No.
you just look at a whole bunch of different, okay.
Yeah, just
All
look
right.
at page 20 in your book and hopefully that starts you on the right track. And did I tell you Chaz will be explaining this much better than me? Chaz will be really, really great.
If you're seriously interested in it, you can still get book copies. And if you go pick up like a Mariner's Guide to Weather, you're going to have like a 3-inch book that is like 8 by 12. And it's just full of information and gives you more examples than you need. Like,
Okay.
I've read it on the Polar Star because we ran out of books because we got extended in Antarctica. So I picked up the Mariner's Guide to Weather and just started reading it. So if you like paper, you pick up one of those guides and it explains everything that you would ever need to know about sea, how to make your own forecasts and predictions when you're out sailing. So it was designed before that specific chart was before we had modern electrical instruments on board. But even the Coast Guard to this day still uses both like electronic charts and paper charts. And every 15 minutes, we're plotting our position, not just digitally, but on paper and checking the weather. So there's some non-rate up there checking the wind speed, the temperature, the barometer every 15 minutes because we're always comparing that data to see if there's a storm popping up and stuff like that. So it's a really cool book to read.
There are references in the back of the student study guide that are also available to you. So I would say check out Samantha's suggestion. Your local libraries, a lot of times will have free, you'll be able to local library.
Where'd they go?
You there, Steve?
Yeah, somehow I got a touch screen here and I touched it somehow and it, shoot, where's everybody go to?
I thought, who was it that was it JT? Who was having trouble logging in? Because if there's not a lot of other questions, we're gonna work with JT Taylor.
Yeah,
Anybody, what's that?
Sean Buckmaster has a quick question real quick.
Go for it.
So if you see this millibars in the, hang on, I have to mute a computer. You see over here in the chat section, the highest sea level air pressure ever recorded was 1083.8 millibars. So we would have to move that decimal over. So we would drop off the 10. So that would be reading 838, correct?
Right. So, you know, and I don't want to get too deep in the weeds on this because you can find examples where you will have, you know, the lowest number is actually the fractions could be. But if you have a weather chart, you're not going to have, you know, the Siberian pressure right next to the I have a hurricane pressure. So I don't want to confuse people too much. So I didn't get too deep into that.
There it is. Okay.
But
It's been a good time, guys.
All right. Thank you, Richard.
See you next week.
All right. Take care, Richard. Thanks for being here. Anybody else is welcome to stay. I just
Thank
made
you.
All right, Monique. Have a good night. Thanks for being here.
Good night. Thank you. Thank you, Samantha.
Thank you, gentlemen. Have a good night.
Good night, Richard. Samantha, I made you co-host and I stopped sharing. So if you want to, who was it? JT was looking for help, or you hear JT?
Night.
Good night.
Night, y'all.
We'll see you next Tuesday. Study hard.
Will.
Was it JT that needed help logging in? Are you there, JT, or can you unmute yourself or no? Samantha, you remember, was it JT that needed help?
Yes.
All right, JT, Samantha's gonna share her screen now and show you how to get into auxiliary classroom. Is that okay, Samantha? Can I ask you to do that?
Yeah, so we have a little bit more to do than that. JT has not even logged into Aux data before.
So what does she need to do to log into Aux data? What is her next step?
Her next step, you can go ahead and share screen.
You want her to share her screen? See you guys.
You can share my screen. Give me permission to share my screen.
You should be a co-host now. You show yourself as co-host. Scroll down to the bottom. You should be able to share screen.
Yeah, let's see.
I'm going to stop recording too.